Today we're revisiting solving exponential equations, except they are going to be at a slightly higher level of difficulty than what we did first time around. All right, day one of chapter 3, we solved equations that look like this. And what we're able to do is express both sides as powers of the same base. So for example, 16 is 2 to the 4th. 8 is 2 to the 3rd. That's 2 to the 12x is equal to 2 to the 3rd. Once you get the bases equal and the exponents cleaned up, you set those exponents equal to each other and solve for what's left. These are pretty low risk of extraneous solutions. These answers do not have to be checked for that purpose, but you may want to check for the purposes of finding arithmetic or algebra mistakes. All right, now what we're going to do is take this and then change it up a little bit. What if it's a 20 instead of a 16? Or if it's a 20 instead of a 16, now you can no longer use the strategy of getting powers of the same base. Okay, so what we're going to do here is we're going to introduce logarithms in order to solve the equation. Now, if you introduce logarithms to the equation, you can introduce logarithms at any base you want. Now, ultimately, good chance you're going to be typing this in your calculator in order to get an answer. What you want to do is keep it as simple as possible. So, simple as possible would be introducing log base 16. And we know if that matches this, it simplifies to just the exponent. And then we divide by 3. And we get an exact solution to be log base 16 to 20 over 3. Now if you're looking for an exact solution, that is the exact solution or one version of how the exact solution could be written. If you need a decimal approximation, with the log base feature on your calculator, you can easily type that in, or you may have to use the change of base formula if you are using an older graphing calculator or just a plain old scientific calculator. Now, before that log base feature was commonplace in technology, it was very often recommended that you would either take log base 10 or log base e, because those are the keys that are already on your graphing calculator. So, just to show you how that plays out, you can take log base 10 on both sides, bring that 3x in front, and then what we're going to do is divide by 3, log of 16, 3, log of 16, and then this would be another version of an exact answer. Part of a decimal approximation is what you're looking for. Typing this in, this will be math. Get that log base function. Base 16, 20, divide that by 3. You're looking at about 0.409. Typing in like this would be log of 20 divided by, and we got the whole quantity, 3 log of 16. And obviously something went wrong. What happened here? Oh, I typed the first one in wrong. Go back and fix that. Clearly they should be the same thing. 20, 360. One thing to keep in mind, say this was a multiple choice question, and all your multiple choice options were in terms of like log base 16, clearly this would be the better option. If all your multiple choice options were log base 10, this would be the better option. If it's a free response, wouldn't matter. Going to a decimal wouldn't matter. Okay. Now, taking this type right here and making it have a few more steps to it. Here, we got that 2 being raised to the t plus 5 power, but there's lots of other stuff on the same side as equals with it. So if we just have that one base with the variable up here, what we want to do is isolate this. We're going to bring over the 4. Divide by the 6. And we don't want to go to any intermediate rounding. If 7/6 was a nice clean decimal, you can go to a decimal, but don't go to any round offs here. Now we're going to introduce logs. Log base 2 of t plus 5. And you can introduce log base anything you want. If that's base 2, keeps it a little bit cleaner to do a base 2 log. If those two match, it reduces to just that. And then we have one step left to get that t by itself. And that would be one version of an exact answer. If you want a decimal approximation, type it in your calculator, follow whatever the round off instructions are. For this one, I believe we should get about negative 4.78. Okay, next two examples. We're going to use a similar strategy. All right, the connecting feature with these two guys is we have variables up in the exponent in two different terms. So the strategy that we used here of isolating this term isn't going to work. Okay, for these two particular problems, we can solve these by factoring. This is the same as e to the x, quantity squared, plus e to the x minus 20 equals 0. It's the same algebraic structure as a squared plus a minus 20 is equal to 0, except that instead of an a, it's an e to the x. So now instead of a and a, using traditional factoring, it's e to the x, and then we need a plus 5 minus 4. Dx plus 5 is equal to 0. Dx is equal to negative 5. And in here, we're not going to get any solutions coming from that. You can't take the natural log or any log of a negative number. So no solutions coming from that branch there. Dx minus 4 is equal to 0. Dx is equal to 4. And we get an exact solution of the natural log of 4. And if the decimal approximation is what you're looking for, you can go to a decimal approximation from there. Okay, another example with a different base. Again, the strategy that we used on the previous page isn't going to work here. It's the variables in two different terms. Okay, this particular equation, similar to this, has a structure that we can solve by factoring. So that is 3 to the x quantity squared, minus 14, 3 to the x, plus 45 is equal to 0. So this has the same structure. It's a squared minus 14a plus 45 is equal to 0. So whatever factoring techniques we would apply here, we can apply to there. So 3 to the x, 3 to the x. Two numbers that multiply to give us 45. Add or subtract somehow to give us negative 14. Minus 9 minus 5. Set each piece of what we factored equal to 0. And we get these two guys as our solutions. That would be the exact solution. If you want a decimal approximation, simply type it into your calculator. All right, next example, I'm going to use a little bit of factoring. Again, but it's going to have a different flavor to it. All right, so we have a variable and a base, and we have a variable and an exponent. So the isolation thing we did here is like twice removed from working. What we do notice here, though, is e to the x is common to both. We have an x common to both. So we can factor this by taking out a GCF. We can take out an x squared, e to the x. That's going to leave 3 plus x equal to 0. And we have x squared is equal to 0. E to the x is equal to 0. 3 plus x is equal to 0. Okay, this one, relatively easy. X is equal to 0. X is equal to negative 3. This is the one we have to think about a little bit. E to the x is equal to 0. Well, one thing we could try is ln of x, e to the x is equal to ln of 0. Well, we can't take the natural log of 0. That's outside the domain for that particular function. The way that I prefer to think about it is if you think about the graph of e to the x, it looks like this. It's never 0. It doesn't cross the x-axis. There are no solutions coming from that branch of the equation. This one and this one are our two solutions. All right, one more example for today. All right, this one here, one thing we would look for is, well, could we express 7 as a power of 5, 5 as a power of 7, or both of them as powers of some other common base? And that cannot be done. So when that cannot be done, it means we need to go to logarithms. This isn't going to factor, actually, I'm sorry, other thing to consider would be, could we factor it like we did the previous few problems? That's not going to work either. So now we're down and we have to introduce logarithms here. This is going to get exceptionally messy when we have exponents in two different places like this, and we have to introduce logarithms. Now, if we introduce log base 7, it's clean there, but messy here. We introduce log base 5, it's clean here, messy there. So there's no ideal way to get this done in terms of keeping the answer as clean as possible. Usually my preference is I'm just going to do log base something else. So I'll do natural log of both sides. You can do log base anything you want. When you introduce logs to an equation like this, it's your call. Now, if it happens to be a multiple choice question, and all the options are in a certain base, then you want to be using that base. If it's a free response or you're going to a decimal anyway, then it doesn't matter. Okay, I'm going to bring that in front. Bring the exponent in front on the other guy too. Now we get both of those x's on the same side of equals. We want to do so without doing any intermediate rounding. We want one final answer we're going to type in the calculator and do one round off in the end. The way to make that happen is we're going to clear parentheses on the left, clear parentheses on the right. Get the x terms to the same side, non-x terms to the other. And something doesn't look quite right here. Double check this. No, that's good. Factor out that x. And then divide by that binomial. And that's one of many different versions you could have for an exact answer. If you wanted a decimal approximation as opposed to an exact answer, when you type this in your calculator, just want to be careful to make sure you get the whole numerator in parentheses, the whole denominator in parentheses. Alternate versions that you could perhaps see, if you were to check this answer in the back of the book, they may bring that 4 up to the exponent, 2 up to the exponent, 3 up to the exponent. Maybe they condense them together. Not really sure. Again, many ways that this could look. In a multiple choice test generator format, this kind of tends to be what they leave the answer as. All right, I believe that wraps it up for today as far as the different variations that we're going to be talking about in equation solving.